Let's continue our discussion of quantum mechanics by revisiting some of the things that we've learned about light. Well, through the double slit experiment, we learned that light has fairly pronounced wave properties. When light passes through two very small slits spaced very closely together, you get a projection of a light-dark pattern of constructive and destructive interference. Only waves can interfere with themselves, creating this kind of a pattern. So this experiment, among others, gives us pretty strong confirmation that light produces certain wave properties. The history of science is full of debates over the nature of light, and even going back to just Isaac Newton, who famously discovered the universal law of gravity after being concussed by an apple, was convinced that light was in fact made up of particles. And so you have this kind of particle wave debate going on for a fair whack of time. Going into the early part of the 20th century, people were fairly well convinced through both the diffraction experiments and others that light was in fact a wave. Enter Albert Einstein, who is most well known for his theory of relativity. It is certainly less well known that he was passed over for a Nobel Prize on that theory. And instead, his lone Nobel Prize came from this paper called The Heuristic Viewpoint Concerning the Production and Transformation of Light, which was published in 1905. And in it, he described and explained what is called the photoelectric effect. The photoelectric effect is simply that when you shine light on a metallic surface, you can eject electrons, and that the ejection of those electrons can really only be explained if light comes in discrete packets or quanta or small bundles of energy rather than a continuous stream. And so what is the photoelectric effect? So again, if you have a metallic surface, metallic substances typically hold their electrons fairly loosely. And if you shine a proper frequency of light on that metal, then electrons can be ejected from that surface. And so what explains this kind of energy interacting with matter to produce, or not produce, but to interact with particles in such a way as to give them velocity? And so one of the things to understand about the photoelectric effect is when you look at the photoelectric effect, it matters what frequency of light or what wavelength you shine on that surface. If the frequency is too low, and so the energy is too low, no electrons will be ejected. If you get a mid-frequency like a green light, you can eject electrons with a fairly low velocity compared to high-frequency light like a purple, which is going to eject the electrons at a higher frequency. If you assume that light is a wave, the only thing that should affect the velocity of those electrons should be the amplitude or the energy of the light. I shouldn't say the energy, but the intensity. But it turns out if you are below the threshold of the right wavelength, the experimental values show you that no matter what the intensity of our red light here, no electrons will be ejected because the energy of the individual particles is too low. And so if we double the intensity on the green light, we don't get faster moving electrons, we just get more of them moving at that same velocity. But at the higher frequencies, the higher energies, those electrons move faster. And so a wave, an assumption of light existing as wave properties, does not explain why intensity rather than frequency affects, or why the intensity doesn't affect, I should say, the momentum of those electron particles. And what Einstein did is he built both the equations and the explanation for why this is the case. Is that light, in fact, comes in little packets, particles of light called photons. And so if you think about this in terms of particle-particle interactions instead of wave-particle interactions, you have a particle of light hitting an electron. The electron then bounces off. It's a game of pool. Think about this like if we have a bowling ball sitting on a table, and if I throw a ping pong ball at that bowling ball, ping pong ball is just going to bounce off. It's not going to have enough energy. And I could throw a handful of ping pong balls at the bowling ball, still isn't going to move the bowling ball. But if I take a baseball and I throw it at the bowling ball, then I'm going to get that bowling ball to move. It was these conservation of momentum particle-particle interactions that explains the photoelectric effect better than light as a wave. So now we have two different experiments, the diffraction experiments and the photoelectric effect. Under one of them, light behaves like a wave. Under the other, it behaves like a particle. And so just like electrons, light exhibits this phenomenon of wave-particle duality. Einstein went further to help us explain what the associated energies of these photons were. And those energies were equal to h, which we saw in our last video is Planck's constant. That's the thing that resolved the ultraviolet catastrophe times the frequency. And of course, Planck's constant is equal to 6.626 times 10 to the negative 34th. So now if we know the wavelength or the frequency of any light, or any particular photon of light, we can then find the associated energy of that particle.